guys, today we are going to be learning about similarity in right triangles. Right triangles have a couple of really neat things that we can do to solve for missing parts that we're going to talk about today. And then you guys have an assignment that goes along with this as well as EDS. So I want to make sure that even if you're absent, you watch this video, you're good to go. We'll jump right in. Similarities in right triangles. For similar right triangles, the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. So what we're saying is if you take one right triangle and you draw an altitude from the right angle perpendicular to the hypotenuse, that's going to be your altitude, that's breaking this whole right triangle into two smaller triangles, this one and this one. And that all three of those triangles, the original and the two smaller ones, all three of those triangles are similar to one another, which is really handy because we can solve for unknown pieces of information this way. So let's repeat that. The altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. For example, if triangle ABC, so that's ABC here, if triangle ABC is a right triangle with right angle ABC and segment BD is the altitude to the hypotenuse, then triangle ABC is similar to what triangle? Triangle ABC is similar to what other triangle? So we're going to make some similarity statements here. So triangle ABC has an altitude BD that is perpendicular to the hypotenuse AC. And we know this is a right triangle, so I'm going to go ahead and put a little 90-degree here to remind us. Okay. And so what we know is these triangles are all similar to each other. So I could say triangle ABC is similar to, let's see, A goes to my right angle, which is B goes to C. So I would say A is still the same. A is going to be corresponding to A. But in this case, my right angle isn't going to be B, it's going to be D. So I would say ADB. Because remember, our corresponding parts need to be lining up. So A is going to be corresponding to A. My right angle is corresponding to my right angle. So B and D are together. And then the new B over here is going to be corresponding to my original C. Okay. And then I could do the same thing. I can say this bigger triangle corresponds to this medium-sized triangle. B is going to correspond with B. D is going to be my right angle, so that's going to correspond with B. And then this missing angle over here is going to be C. Okay, so I would say triangle ABC is going to be congruent to triangle BDC. Not only that, but I can say ADB is congruent to BDC. We're going to use that information to solve for something called the geometric mean. The geometric mean is going to allow us to solve for any missing parts of our triangle. So we're going to talk about just the geometric mean of two numbers, and then we'll use that formula to help us find the geometric mean when we're dealing with the altitude, or we'll use another version to help us when we're solving for a leg. I'm going to use, I believe, 4 different colors of highlighter for this. So grab yourself some highlighters, preferably the light colors so you can see what's going on. And we're going to go ahead and hop in. So before we get into the triangles, we're going to talk about for any 2 positive numbers, so they have to be positive. For any 2 positive numbers, A and B, those are our 2 numbers, the geometric mean is the positive number x such that A divided by x is equal to x divided by B. So our geometric mean x, we can find it for the 2 numbers A and B by saying A divided by x is equal to x divided by B. Note that when we solve this, we end up with x is equal to the square root of A times B. Move that off the screen. Okay. All right, so we're going to now use that information to make some observations about the triangles themselves. And this is where the color coding is going to come in. The altitude to the hypotenuse of a triangle divides the hypotenuse into 2 segments. The length of the altitude is the geometric mean of the lengths of those 2 segments. So remember, geometric mean up here, that was x, was the 2 diagonals that are the same. And so what this is saying is we're going to take one part of the hypotenuse and divide it by x and set it equal to x divided by the other part of the hypotenuse. And that's where we'll grab some color coding. So 3 colors for now. I go ahead and do blue, pink, and green. Sorry. All right, so I'm going to make my altitude pink. Okay, so my altitude I'm going to make pink. My altitude is the geometric mean. Okay, so I put that in the position of my formula up here for geometric mean. My altitude is pink, and then I'm going to break my hypotenuse into 2 segments. There's the segment that's on the left of the altitude and the segment on the right of the altitude. Okay, so we're going to go ahead and we're going to say segment 1, which we'll call part of hypotenuse. And we're going to divide that by the geometric mean, which in this case is the altitude. So this is the same formula we're using here. We're number divided by the geometric mean. And then we're going to put, once again, the altitude up here. Over the second part of the hypotenuse. Say part of the, just make it grammatically correct, hypotenuse. So I'm going to go ahead and make my part of the hypotenuse, my CD, as green. Okay. And then once again, my altitude is pink, which is my geometric mean. And that's over the second part of the hypotenuse, which is my blue DA or 80. Okay. And up here you could color code that too. The geometric mean we could say is our pink, which is our x. And we have our A and B, which are those other parts. So the numeric does match up to the triangle. Okay. And we can do this if we were doing, let's say, a proof, which we will be doing soon. We would put the names, the generic names of the segments before we plug numbers in to solve things. So for here, if I'm doing part of the hypotenuse, this green part, I would put CD, because remember I name a segment going one endpoint to the other, over my altitude, which is BD, is equal to my altitude of BD over my smaller part here, which is DA or AD. Okay, and we would color code those the same. So I really want you guys to use the color coding to your advantage when you're quizzing or doing your homework, so you get that practice lining things up. And you see that even when we change stuff, these problems are very similar. Okay. All right, so we're going to take part of our hypotenuse over the altitude is equal to the altitude over the other part of our hypotenuse. And this is what we're going to do when we're dealing with the altitude. Okay, so in this case, we're dealing with the altitude. We're going to do something different when we don't know the altitude and we don't care to know the altitude, or we don't need anything to do with the altitude. So this is our first one. Now let's come down here to finding geometric mean with a leg. So if you remember back to Pythagorean theorem, when I have a right triangle, I have a leg, and a hypotenuse. So this is saying if I know one of the legs, I can use this formula that we're about to take notes on to find missing information. So this says the altitude to the hypotenuse of a right triangle divides the hypotenuse into two segments. So same as before. The length of each leg of the triangle, the length of each leg of the right triangle is the geometric mean of the length of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So there's a couple things we're going to break down with our color coding. First off, let's keep the geometric mean pink again. Okay, so that it matches up with our other examples. And let's break this down. It says the length of each leg of the right triangle is the geometric mean. So the leg is going to be the geometric mean. So we're going to do two examples here, one for each leg. So in this example, my leg I'm going to use is BA. And then over here on this example, I'm going to use leg CB. Okay? And so I'm going to make those ones pink, and I'm going to show you that we're putting those into the same formula as before. So we're going to go ahead and remember that our geometric mean goes here and here. Our geometric mean goes here and here. So we're keeping that consistent. But in this case, it's the geometric mean of the lengths of the hypotenuse. So we need the whole thing, the whole hypotenuse. So all the way from C to A. The whole thing. So not a part this time, but the whole thing. Okay? And remember, we're going to put that here. Okay? Same thing over here. Doesn't matter which leg we use, we're going to start with the whole hypotenuse. So that's going to go right here. Okay, and the other part, and this is where things get different. So I'm going to use green this time, or sorry, not green. We already used green. I'm going to use yellow this time instead, just to give you. You know what? I'll stick with green. Okay, so I'm going to go ahead and use the. Let's look at this. Adjacent to the leg. So we're using this pink leg. I need to figure out which part is adjacent. Is CD adjacent to BA, or is DA adjacent to BA? And we know adjacent means they're next door neighbors. They're right next to each other. So we're going to say that DA is my adjacent to my leg. So that's going to be right here. And then over on this leg, I would no longer say DA is adjacent. Those are no longer touching. On this leg, CD is the adjacent leg. Okay. All right, so let's look at this really closely. Blue is my hypotenuse, so the whole thing. So let's highlight the word hypotenuse. Blue is my hypotenuse. Pink is my geometric mean, which is one of my legs. I have to pick a leg. So my geometric mean, my pink, is one or the other of the legs. So we made those pink. And then green is going to be the segment of the hypotenuse that is adjacent to that leg. That's wordy, but that's where the green came in. Okay, so pink is the leg, and that's our diagonals. Blue is the whole hypotenuse. And then my green is the segment of the hypotenuse, so just one part or the other of my hypotenuse that is adjacent to my leg, that is adjacent to my pink, my geometric mean. Okay, and so we've got the same setup for those. We're going to go ahead and add these letters in. So my whole hypotenuse here would be AC or CA. Okay, and then my leg that we're picking, this shorter one right here, the pink one, is going to be AB. And it's AB in both parts. So notice in all of these examples, those diagonals are the same number or the same value. And then in this one, our smaller segment is AD. So we're going to go ahead and put AD for our green, because that smaller segment is now adjacent to this side right here. And then over here, we're doing similar, the whole hypotenuse, so AC, over the leg we highlighted. So this one would be CB, which would match up with CB. And then this time, we're not using AD, we're using CD. All right, you're going to use these formulas we just did to do the math at the bottom. If you think you're prepared to go ahead and pause the video and try these problems on your own. If you want me to walk you through them, stay tuned, like I said, or pause and come back and check your answers. We've got three things we're going to be able to do. We're going to be able to take two numbers and use this formula to solve for the geometric mean. We're going to be able to solve for a missing part using the altitude, geometric mean theorem with the altitude. Or we're going to be able to solve for a missing part using the geometric mean for the leg theorem. Okay, so those are the three things we should be able to do at the end of this practice. And then, like I said, you have an assignment that goes along with it. All right, so for the let's practice, it says find the geometric mean of the two numbers. So let's use our same letters again. Let's use our colors again. Let's use our green for our first number and our blue for our second number. And let's remember that geometric mean, our x value, is the pink color. Okay, and so we're going to match this up. I'm going to pull it down for just a second. We're matching this up with a over x equals x over b. But in this case, a is 4 and b is 9. So we're going to use this formula to solve for x. Okay, so we're going to go ahead and we're going to do 4 over x is equal to x over 9. And we can put our color coding in, so when we look at this later on a homework assignment, we have a really carefully color-coded process to use as an example to help us out. I know a lot of you guys skip this part. The color coding part really does make stuff jump out to you when you're frustrated or confused. So I would definitely use it. All right, in order to solve a proportion, we already practiced this last set of notes. We're going to do cross multiplication. So I'm going to say 4 times 9 is equal to, that's my first diagonal, is equal to x times x, which is my second diagonal. Now, there's some algebra that goes into this once again that we need you to know. For example, I need you to have memorized that x times x equals x squared. Okay, if you haven't memorized that yet, it is beyond important at this point for you to memorize that. So x times x is equal to x squared. 4 times 9 is equal to 36. And now here's where an important math skill comes in. X squared is the inverse of the square root of x. So if I want to undo a x squared, I'm going to square root both sides of my equation. A square root and a square are inverses. They cancel each other out, leaving behind just x. The square root of 36 is 6. So my geometric mean is 6. Okay, go ahead and try 15 and 20 on your own. Pause the video and come back for the answer. All right, hopefully you guys are just coming back to check this out. We've got our 15 and our 9, and our 20, which are our A and B. And then we'll have x, which is our geometric mean. So we're going to set up the equation same way. 15 over x is equal to x over 20. We get 15 times 20 is equal to x squared. 15 times 20 is 300. And to get x by itself, I need to square root both sides. But I want to show you something, and this is an important thing for you to know. If I take this and I do 300 and I square root 300, I get this. A lot of times when you are doing problems on EDIA or a test of any sort, they are going to ask you for the exact answer. I cannot give the exact answer for this. It is an irrational number, meaning if this screen was bigger, it would just go on and on and on forever. There's no repetition. There's no stop. It just keeps going on. So we would round this, and I would get 17.3 if I rounded to the 10th place. So I would end up with x is approximately equal to 17 and 3/10. Or if they said go to the hundreds place, you go further, and so on. But most of the time, they're going to want to know the exact answer. So we need to do a quick review of finding a simplified radical. So since we know 300 isn't a perfect square, I'm going to simplify it. I'm going to take this onto the back and do a quick review of simplifying radicals for you. I would strongly suggest, and I'll give you an EDIA on this, practicing simplifying radicals. So we're doing the square root of 300. I'm going to go ahead and flip my paper over so we have plenty of room. And I'm going to write simplify. I guess I'll write simplifying radicals. And this word radicals just means square roots, cubed roots, fourth roots, any kind of root. Okay, so you could put in parentheses roots if that helps. Okay, so simplifying radicals is going to be a process of seeing, are there any perfect squares inside your radical? So here I'm going to give you a couple ways of doing this. I have the square root of 300 is the problem we're trying to simplify. And the first thing I would want to do is look at this and go, do I see any just obvious perfect squares in there? And if I do, I can kind of skip forward. So I'll show you that method, but then I'm also going to show you what do I do if I don't see any perfect squares. So when I look at 300, I see 3 times 100. And my rules for radicals tell me that the square root of 3 times the square root of 100 equals the square root of 300. We just multiply what's underneath, which means I can also pull them apart like this. Okay? And now that I've pulled out a perfect square, I know what the square root of 100 is. Square root of 3 is an irrational number, but the square root of 100 is 10. And so my simplified radical would pull my whole numbers out to the front and then leave behind the most simplified radical I could get, which in this case was that square root of 3 was left over. I can't simplify that. So I would get 10 square root of 3 for the answer to the problem. So let's move that over and then I'll show you another method to do this. So before I forget, we could put, now this would be an equal sign since I didn't round it. and I could put 10 square root of 3 as my solution. And you're going to need that one more often than the rounded one, so I'm going to box that one. Okay, remember if you round, you got to use the wavy approximation instead of the straight equal sign. All right, now I'm going to show you, what if you didn't see that it was 3 times 100? What if it's something you don't see? So I'm going to show you a way of simplifying radicals called upside down division. We're going to take this number 300, and instead of putting a long division sign, we're going to put an upside down long division sign like so. And we are going to divide by prime numbers. And knowing at least your starter prime numbers by heart is super important. When I taught middle school, I definitely had my students memorize these. If you haven't, it would be worth your time. First, we'd have 2, and then 3. 4 is not a prime number, it's divisible by 2. 5. 6 is not a prime number, it's divisible by 2 and 3. 7. 8's not a prime number, 9's not a prime number, 10's not a prime number, but 11 is. 12 is not, but 13 is. And they keep going. Okay? Usually you don't have to go much further than 13. That 2, 3, 5, 7 is where most of the problems you're going to deal with are going to be at. So even if you can remember the first couple, that gets you started. And remember that prime number just means that it's not divisible by any number other than itself. So the only thing you can divide 2 by and get a whole number answer is 2 or 1. Okay, so that's what prime numbers are, just as a quick reminder. We're going to start with 2 and work up from there. So even if you know, like for example, 3 is there, I'm not going to divide by 3 first. I'm going to start by 2. I'm going to use 2 over and over again until I run out of 2's. Then I'm going to go to 3. And you'll see that these leaves our numbers in order and keeps us from making mistakes. So please, please, please don't go out of order, even though, yes, I see a 3 there. We're going to go 2 and then 3, and then if we have to, 5. And we keep going through these until we get to a prime number at the bottom, which will make sense in a second. So my first prime number is 2. I have to ask myself, is 300 divisible by 2? It's an even number, so it is. 300 divided by 2 is 150. 150 is still an even number, so I know it's divisible by 2 again. 150 divided by 2 is 75. 75 is no longer an even number, so I'm done with 2. Now I'm going to try 3. And I just keep moving through my prime numbers. As I run out of one that works, then I move to the next one. So since it's no longer divisible by 2, I'm going to check 3. 75 divided by 3 equals 25. 25 is not divisible by 3, so now I'm going to bump up to 5. And then I say 25 is divisible by 5. 25 divided by 5 equals 5. Once that bottom number is a prime number, which it is, I'm done with my upside down division. Now I want to make some perfect squares so that I can simplify the radicals. So I notice that 2 times 2 is going to give me a perfect square, because that's what a perfect square is. It's just a number multiplied by itself. 2 times 2 is 4, so I end up with the square root of 4 times, I don't have anything to partner the 3 with, so it's just going to stay by itself, times, I've got partners here, 5 and 5. 5 times 5 is 25. So we took the 2's, multiplied them back together and got 4. The 3 is all by itself, so it stayed 3. And 5 times 5 is 25, so it's right there. Okay? Now we can simplify the radical. We can say square root of 4 is 2. Square root of 3, I cannot simplify. Square root of 25 is 5. I can multiply my outside numbers, my coefficients together. 2 times 5 is 10. Leave the square root of 3 behind. It's not simplifiable. So I get the solution just like before of 10 square root of 3. Just like I did over there. Okay, so sometimes you'll be able to see the perfect square in your head and pull it apart like so. Sometimes you'll be like, oh, I can't remember if there's a perfect square in there. I'm going to do upside down division. And I can simplify it one perfect square at a time. You'll pull out, like I said, pairs of numbers. So the square root of 2 times 2 is 2. The square root of 5 times 5 is 5. And then the square one that does not have a partner stays inside the radical. Okay, so that's a quick overview of simplifying radicals. We'll look at a couple more problems like that as we work through the examples. So flipping back to the front, I have that my geometric mean, which in this case is pink, is x is equal to 10 square root of 3. All right, for this next example, it says to solve for x. So what we need to do is we need to look at this and say, it's not just two numbers, so I'm not going to use this example. That's just when I have just two numbers, which we did here. So I need to look at it and say, do I have the altitude or do I have the leg? Okay. And so if I'm looking at example A here, they gave me 6 as my altitude. So in this case, I'm going to use the altitude because that's the one they labeled. Okay. And so if they use the altitude, then I need to come up here and go, okay, this was, the altitude is the pink part, the geometric mean. And then I need one part of the hypotenuse compared to the second part of the hypotenuse. So I'm going to take my green and my blue. And I'm going to say one part of the hypotenuse. And I'm going to compare it to the second part of the hypotenuse. Okay, and now I've got my color coding, I've got everything lined up. I can carefully pull information in to solve. We'll write the equation here, but as usual, they didn't give us enough room, so we'll flip it over the back to solve. So let's look at this. We're using altitude, so I'm not going to use the leg one, I'm going to use altitude. It's my part, so my green over my altitude is equal to my altitude pink over my other part. So we're going to say green is x over pink is 6 is equal to pink is 6 over my other part, blue is 4. And I can color code that once again so that when I'm looking back at my notes, I can see where everything comes from. I don't have to guess and get frustrated. Okay, so really using the colors is going to be hugely helpful to you. So we're going to take our x over 6 equals 6 over 4 to the back and solve. Okay, so let's go ahead, come over to the back. I've got x over 6 equals 6 over 4. I know that this is a proportion and I can solve for a missing part by using cross multiplication. So I'm going to say x times 4 is my first diagonal. And I'm going to set that equal to 6 times 6, which is my second diagonal. X times 4 is just 4x. 6 times 6 is 36. I divide by 4 on both sides. And I get x is equal to, let's see, 36 divided by 4 is 9. Okay? So I'm going to come back to the front with my x equals 9. My box around it. There were no units of measurements or word problems I need to work for. It just said solve for x, and I know x equals 9, which was my part of my hypotenuse. So we'll put the green there. Go ahead and pause the video and try B. But I want you to look at it and say, are we given the leg or are we given the part of the hypotenuse? If you don't know yet, stick around. I'm going to look at this and see how we had the altitude here, the pink part here. If you look at this one doesn't have anything labeled. So that's a clue right off the bat. They don't want us to deal with the altitude because there's nothing there. There's no letter, there's no number, nothing's there. So that makes me think we're going to use the leg. So I'm going to go ahead and I'm going to notice that this leg right here is x units long. Okay. So when I'm deciding which one of my theorems to use, I'm not going to use altitude anymore. I'm going to use the leg because they gave me a leg to deal with. They did not give me the altitude. Okay, and when I do leg, I do the whole hypotenuse all the way across. So let's get my blue and do the whole hypotenuse all the way across. So from here to here is blue. And then for my green, I have the segment of the hypotenuse that is adjacent to the leg. So my leg is here in pink. And I need to decide, is 3 or 9 adjacent to this pink part? So hopefully you can see that 9 is the part that's adjacent to the pink part. And so those are going to be our numbers we use for our proportion. So we've got, looking at this, the whole hypotenuse, which in this case, let's see, if I've got 3 here and I've got 9 here, that tells me the whole hypotenuse is going to be 12. Okay, that's my segment addition theorem from before. And then I'm going to put that over my geometric mean, which is my leg, which is x. And that's equal to my leg over my part of my hypotenuse, which is just the 9. So I have 12 over x is equal to x over 9. And I'm going to turn that over to the back and solve. So 12 over x, x over 9. So let's go ahead and write that. I've got 12 over x is equal to x over 9. Going to now cross multiply. 12 times 9 is equal to x times x. X times x gives me x squared. 12 times 9, let's see, 9 times 10 is 90. 9 times 2 is 18, so that's going to be 108. And this is where I have to remember, gosh, how do I get rid of that square? I just want to know what x is. I don't want to know what x squared is. So I remember, to undo a square, I'm going to square root, because squares and square roots are opposites, so those cancel out. But I have to square root both sides, just like when I add both sides or subtract from both sides. Okay? And so I end up with x is equal to whatever the square root of 108 is. We could get lucky and that's a perfect square, or we could have to simplify. So let's try it. 108, do second square root. That is not a perfect square, so we're going to round this to 10.4. If we were asked to round, we would make an approximate equal sign. Okay, so our squiggly one is equal to 10 4/10. But I want you to simplify the radical. I want you to have more practice with what we did over here. So let's take 108. Move this down so we have an example. And just like we did here, let's do some upside down division for 108. We're going to start with our smallest prime number and work our way through. So since this is an even number, I know it's divisible by 2. 108 divided by 2 is 54. Since 54 is still an even number, I can divide by 2 again. 54 divided by 2 equals 27. 27 is not an even number, so I know 2 is not going to work. My next prime number is 3. So I have to ask myself, is 27 divided by 3? If you don't know, then grab a calculator and say 27 divided by 3. If it gives you a whole number, good. If it doesn't, then you'd move up to the next prime number. In this case, 27 divided by 3 is equal to 9. I know 9 divided by 3 is equal to 3. And I know I can stop now because I have a prime number at the bottom. So we keep dividing until the bottom number is a prime number. And then we're going to take these out in pairs. So I have 2 times 2. So I have the square root of 4. And then I have 3 times 3. So times the square root of 9. And then I have this little one right here all by itself. It does not have a partner. Well, I know the square root of 4 is 2. I knew the square root of 9 is 3. And I know I can't simplify the square root of 3. Now, when you take them out in partners, you can just say, oh, a pair of 2's is 2, a pair of 3's is 3. I'm writing the radicals so you can see where those numbers come from and you'll go, why is she doing math magic again? So 2 times 2 is 4 and the square root of 4 is 2. 3 times 3 is 9 and the square root of 9 is 3. And then this 3 doesn't have a partner, so it just stays 3. We got this one here. We got this one here. We got this one here. Nothing came from nowhere. Everything's right there. Okay? I know 2 times 3 is 6. So my solution for this problem is 6 square root of 3. So let's come back to the front. And we get the answer is x equals 6 square root of 3. And that's our exact answer. If we have to round, it's no longer an exact answer. Okay, so they had us solve for the part right there. There you go. Okay, so we've done 2 where they gave us 2 numbers and we solved for the geometric mean. We've done 1 where they gave us the altitude and we solved for a missing part. And we've done 1 where they gave us the hypotenuse and part and we solved for the leg. Oops, and I did the wrong color there. My bad. Hopefully you caught that. I'll go ahead and make that a pinkish color. Sorry about that, guys. All right, well, let's move down over here and continue. I'm going to do the next ones a little bit faster just because this video gets getting crazy long. All right, so let's look at this. Right off the bat, I see an altitude. So I'm going to make my altitude pink, and that's going to be my geometric mean. And when I have an altitude, then I'm able to just use the left part of the hypotenuse and the right part of the hypotenuse to solve. So I'm going to take my part of my hypotenuse and divide it by my altitude, make that equal to my altitude divided by my part of my hypotenuse. Same thing again. I've got my green divided by my pink equal to my pink. Oops, I switched up my colors this time. Sorry, guys. Divided by my blue. No, I didn't. Alright, so I'm going to go ahead and solve that on the back. 2 over x equals x over, actually, I can solve that here. That's not very long. 2 times 8 is equal to x times x. That's 16 equals x squared. I square root both sides. The square root of 16 is 4. The square root of x squared is x. So I get my solution is x is equal to 4. Okay, once again, that color coding just set me up easy peasy. Looking at this next one, do I have a leg or an altitude? I have that middle number right there. So that's my altitude. And then once again, we've got the part of the hypotenuse compared to the part of the hypotenuse. So we're going to take the part of the hypotenuse, 23, over the altitude, 60, is equal to 60, the altitude, over x, the other part of our hypotenuse. My altitudes are those diagonal matching numbers. And then I have my parts in my blue and green. Okay. And so we can do 23 times x is equal to 60 times 60. That gives me 23x is equal to 3600. I'm going to let you guys get a decimal on this one because I don't want to make this video long enough to talk about getting a fraction from this. We can come back to that later. So if you get 3600 divided by 23, that is 156, and we'll say 5/10. Notice that I used the squiggly equal sign because it's an approximation. I had to round. Okay. And that was my blue color. All right, 2 more problems and then we're good to go. These ones are going to take a little extra thought. They're not always going to give you specific information. Looking at this problem, it says solve for x and y. So right off the bat, I know I have to do more because they gave me more than one missing part. And then I see that they gave me the legs. Okay, this is a leg and this is a leg. They did not give me the altitude, nor are they asking me to solve for the altitude. So right off the bat, I'm hoping you go, I'm not using this one. I'm using this one because they gave me legs. And in fact, I'm going to use it twice because they gave me this set and they gave me this set. So I'm going to set that up twice. But my problem here is that when I use the leg theorem, I need the whole hypotenuse, and I do not have the whole hypotenuse here. So I have to look at this, and I have to think, gosh, how am I going to find the hypotenuse of this right triangle? Wait a second, let me think back to my previous math classes. I know if I have this leg and this leg, I can use the Pythagorean theorem to solve for the hypotenuse. So before you use the geometric mean theorem, they want you to solve for the hypotenuse using the Pythagorean theorem. And they're not going to tell you that because they're asking you to connect your prior knowledge, things you already know how to do, with this problem. So we need to do a squared plus b squared equals c squared, which is Pythagorean theorem. So I'm going to say 20 squared plus 15 squared is equal to c squared. Even though they didn't ask me to solve for c, because I need c, I need the hypotenuse to use my geometric mean leg theorem. Okay, so even though they didn't tell me to solve for the whole thing, I have to do so in order to be able to get to the other information. So 20 squared is 400. 15 squared is 225 equals c squared. 400 plus 225 is 625. To find the square root of c squared, I'd have to square root it on both sides. The square root of 625 is 25. So I get that my hypotenuse, which I called c, is 25. And let me double check that math. 625 second square root 25. Okay, so now I know my entire hypotenuse, so we're going to name that blue to keep it consistent with our notes, is 25. So I can label that as 25. And I know that my part, this is where I'm going to pull in some extra colors, maybe, we'll see. I have a leg here that's 20, and I'm going to compare that to the part of my hypotenuse that's adjacent to that leg. So how do I do this? I am going to say full hypotenuse over leg is equal to leg over part, adjacent part. So I've got full hypotenuse is 25 over leg, which is 20, is equal to leg, which is 20, over y, which is my part. Okay, and you could do the colors first. I'll do the colors first for the next one just so you can see what I'm saying. I've got blue over pink is equal to pink over green. And so I'm going to take this to the back because clearly I'm out of room. 25 over 20 equals 20 over y. So 25 over 20 is equal to 20 over y. 20 times 20 is 400. 25 times y is 25y. I know that there's 4 25s in 100, and that's 400, so that's going to be 16 is equal to y. Okay, if I divide by 25, I get 16 equals y. So I'm going to come over here. It's been still too long. My light's turned off. I'm going to come over here, and I'm going to put y equal to, I got distracted, let's double check, 16. And I'm going to go ahead and box that. But they didn't just ask me for y, they asked me for x as well. So now I'm going to use a different color even though it doesn't match up as well, just so you can see. So instead of using, let's use orange instead of pink this time. So I'm going to use orange here for this leg. And then my adjacent leg to that I'll use yellow for. This is my adjacent leg. Now, it won't match up to our pink and blue and green above, but I didn't want it to get confusing with the two pinks and the two greens. So we're going to do our, let's look back up to here. Our whole hypotenuse is still blue. So we're still going to do our whole hypotenuse, which is 25. But now my leg is 15 instead of 20. So I'm going to put geometric mean is 15 over, and then x is what I'm solving for. So let's take that to the back. 25 over 15 is equal to 15 over x. Actually, we still have the blue here. And we still have, but we turned the green into yellow to keep it more color specific. And then we turned the pink into orange. So I just want to get those there for you. So 25 over 15 equals 15 over x. 25 over 15 equals 15 over x. 25 times x is 25x. 15 times 15 is 225, I believe. Let me check. 15 times 15 equals 225. And we need to divide by 25 on both sides. Yeah, x is equal to, let's see, 25 is going to go into 208 times one more, so that would be x equals 9. So I come back over here, and I get x is equal to 9. And I'm going to put that in the box. So my y was my green, and my x was my yellow. All right, last problem, and then we can put an end to this video. All right, if I'm looking at this, I'm hoping you look at this and see what you know. I see some segment addition that's coming up. I see that I don't have the altitude, but I do have a leg they want me to solve for. So I'm going to put my leg as pink again, because that's going to be my geometric mean. And then I'm going to put the entire hypotenuse from one end to the other as my blue, which in this case is green. I don't know why I said green, which in this case is 8. And then I'm going to compare that to my part of my hypotenuse that is adjacent to the pink. You're going to want to use 2 because it's the one they gave you. But 2 is over here. It's not adjacent to the pink. So what I need to find is that. So I'm going to use my segment addition postulate and go, hey, I know if the whole hypotenuse is 8 and this little bit over here is 2, then the missing part is 8 minus 2 is 6. So I would get this as 6. Okay. And the way you could do that, if you can't remember, segment addition postulate, a plus 2 equals 8, and solve. All right, and now I'm going to use, let's see, I'm going to use the leg theorem again because it's a leg, not the altitude. And I'm going to go ahead and say the whole hypotenuse is 8 over x is equal to x over my part, which is 6. I can say x times x is x squared, which is equal to 8 times 6 is 48. I can hope that that's a perfect square, but I don't think it is. So let's check my math. 8 times 6 equals 48. Second square root. I need to go simplify a radical. So we're going to go ahead and throw a square root sign around both sides. And I get x is equal to, and I need to figure out what the simplified version of the square root of 48 is. So let's flip this over, give us one more example. So I've got 48. Upside down division, that's an even number, so I'm going to divide by 2 and get 24. That's an even number, so I'm going to divide by 2 and get 12. Also an even number, so I'm going to divide by 2 and get 6. Also an even number, so I divide by 2 and get 3. So 48 divided by 2 is 24, divided by 2 is 12, divided by 2 is 6, divided by 2 is 3. Notice you end up with a lot of 2's and 3's when we do this process. All right, just like before, I want to pull things out in pairs. So I've got a pair of 2's. 2 times 2 equals, we're going to say square root of 4. Got another pair of 2's. 2 times 2 equals, we're going to say square root of 4. Notice I didn't take all the 2's out together. I take them out in pairs. That way I can square root them. Once again, my friend 3 has no partner, so he's going to stay all by himself. The square root of 4 is 2. The square root of 4 is 2. Square root of 3 cannot be simplified, so it's just 3. 2 times 2 was 4. Square root of 3. So my simplification of the square root of 48 is 4 square roots of 3. So I'm going to come over here. I'm going to write 4 square roots of 3. And I'll make a note that my work is on the back. So that if I'm looking at my notes later and I'm like, how did I get that? I remind myself, okay, look, flip it over and look. Once again, this was my hypotenuse over my leg equal to my leg over the part of the hypotenuse. And my x was, in this case, the leg. So I solved for the leg and got x equals 4 roots of 3. And remember, when they're touching like that, that's multiplication. So this is 4 times the square root of 3. Whew, that was a long set of notes. Hopefully you stuck with it. You checked your work and everything's making sense. You have your this or that worksheet to work on, as well as I will have posted within a few minutes of making this video some media to go along with practicing geometric mean, as well as practicing geometric mean with triangles, as well as simplifying radicals. So make sure you check your media. Have a wonderful day.